Hello everyone. Today we are going to find the stresses in composite bars. Composite bars are made of two or more materials. So first let me represent a composite bar. So it is made of two materials. So we will take steel as one material. So that is represented by this black. And the second material can be brass. That is represented by the blue. Now, what I'm actually going to do is I'm going to subject this bar to a load that is represented by this red in color. Okay, that's not red. So here we go. So it is subjected to a load of magnitude capital P right at the center. So the question is whether the two bars, steel and brass, they are secured to one another, whether they are actually going to take the same stress or not, whether they will be taking the same load or not. The answer is definitely no. Let me give an intuitive example. Just imagine that you are lifting an object. The question is whether your muscles, the tissues, and the bones, will they be carrying the same magnitude of load? Definitely not. Your bone will carry more magnitude of load compared to the muscles and the tissues. Uh, the same for radial tires. Say, for example, you have got the steel wires inside your radial tire, and the steel wires will be taking more magnitude of load, okay, inside the radial tire. So, load by definition is degree of interaction. More the degree of interaction, more the load. So, in this case, a steel is going to interact with the load in a greater fashion compared to brass. So, steel is going to take more load, and therefore, steel is going to take more stress. Okay, fine. So that leads us to the first equation, that is the total load, which can be denoted as capital P, should be the sum of the load that is carried by steel and the load that is carried by brass, and the two loads will not be the same. We know stress is load over area. So load should be stress into area. So I just have to add the suffix. So let me rewrite the above equation here as load of steel should be equal to stress of steel into area of steel. It's a cross-sectional area plus the stress of brass into area of brass, cross-sectional area, is equal to capital P. I can even rewrite this equation further as stress in steel into area of steel plus stress in brass into area of brass minus capital P should be equal to 0. This is going to be our first equation. Okay, I can call this as equation 1. Now, if you look at this equation 1, I will put tick marks for the known values. Definitely you know what is the cross-sectional area of steel, and you also know what is the cross-sectional area of brass, and you know what is the total load that you are subjecting this entire structure to. So the unknowns are, these are the unknowns here. The unknowns are the stress in steel, that's one unknown, and the stress in brass, this is the second unknown. So if you have got two unknowns in an equation, you just need one more equation, and you can just solve the two equations simultaneously in order to find the stresses. So how do you come up with the second equation? If you look at the deformation, both the bars, steel and brass, they are going to get deformed by exactly the same amount because they are secured to one another. So the deformation is represented by this dashed line here. So both steel and the brass, they are getting deformed by exactly the same amount. So let us say that the deformation of steel is represented by del L suffix steel. The deformation of brass is represented by del L suffix brass. Now we know that del L of steel should be equal to del L of brass. You will be tempted to use a strain of steel should be equal to strain of brass. That's perfectly fine because both have the same length, but not all the times the composite bars will be having the same magnitude of length. Sometimes the length can be different. In such cases, it would be best if you just use this equation: change in length of steel is equal to change in length of brass. So that works really best for you. Okay, now we know Young's modulus is stress by strain. I can write this equation as strain into Young's modulus is equal to stress. We know strain is change in length divided by original length into Young's modulus is equal to stress. So that brings us to the equation for change in length. So change in length is equal to sigma into L divided by Young's modulus. So all I have to do now is add the suffix. So for steel, I can just bring this equation here. For steel, it will be stress in steel into length of steel divided by Young's modulus of steel. That should be equal to stress in brass into length of brass divided by Young's modulus of brass. So if the two lengths are going to be equal, so I can cancel these two terms. If length of steel is equal to length of brass, so I can now bring this Young's modulus here and bring this Young's modulus here. I can write this equation as stress in steel into Young's modulus of brass should be equal to stress in brass into Young's modulus of steel. So now I can bring this guy to the left side. So stress in steel into Young's modulus of brass minus stress in brass into Young's modulus of steel, and that should be equal to 0. So that's going to be our equation number 2. Now, if you look at equation number 2, you know the value of Young's modulus of brass, so I'm putting a tick mark for that. You also know the equation for Young's modulus of steel, and just putting a tick mark for that. So now you can find the value of stress in steel and the stress in brass by solving the two equations, 1 and 2, simultaneously. You can just solve them simultaneously just by using your calculator. You can just solve them to find the stress in steel and stress in brass. As I told you, not all the time this length is going to be the same. Sometimes the length can actually be different. Say, for example, in some cases, you can have composite bars like this. Maybe this is the foundation. And you may have steel bars at the center. Okay, and you can have a copper bar on the left side. There can be one more copper bar on the right side. So this is steel and these two are copper bars. Now clearly the length is not the same, and this can be subjected to a load. Say, for example, I can represent the load, maybe a block. This can be subjected to load something like this. Okay, so the lead one, it's a kind of uniformly distributed load that I'm trying to represent. I'm not able to draw a block. I really wanted to draw a block, but yeah. So in this case, clearly the length is actually different. So the length of the length of copper is not going to be the same as the length of steel. So in such cases, what you have to do is you can just do exactly the same. You can say the change in length of steel should be equal to the change in length of copper, the first copper, as well as the change in length of the second copper bar. Okay, so you can still use the same equation and you can just solve them. For the equation number 1, the total load will be equal to load carried by steel plus the load carried by the first copper bar plus the load carried by the second copper bar. If these two are equal, so you can just multiply this by twice, right? Or you can alternatively think in terms of area perspective. You can just multiply the area 2 times and treat that as a single copper bar. You can still solve the problem. it will work perfectly fine. Hope this is useful. So thank you all for your patience.